Right now, if you look around at any reasonably diverse group of people, you'll see an enormous range of skin tones, from very deep to very pale, with basically every shade in between. Most people never really stop to ask why that variation exists in the first place, because it's just always been part of the visual backdrop of being human. But there's a real, well-documented evolutionary story behind it, and it starts from a pretty surprising place. Every single human being on the planet today descends from ancestors who, tens of thousands of years ago, had dark skin. Lighter skin isn't some separate, independent origin. It's a relatively recent evolutionary adaptation that happened after certain human populations migrated into specific environments, and the reasons behind it are a lot more interesting than most people assume. So let's dig into it properly. How did some ancient humans end up with lighter skin when our entire species originally started out with dark skin? And what was actually driving that change at a biological level? Let's start with why humans had dark skin in the first place, because that's really the necessary starting point for understanding everything that came afterward. Early humans evolved in Africa, in regions with intense, near-constant sun exposure throughout most of the year. Darker skin, produced by higher concentrations of a pigment called melanin, offers real, meaningful protection against ultraviolet radiation from the sun. Melanin absorbs and scatters UV rays before they can penetrate deeply into skin tissue, reducing the risk of sunburn, skin damage, and specific health problems tied to excessive UV exposure over a lifetime. But there's a more specific, less commonly discussed reason dark skin mattered so much in this particular environment, and it involves a nutrient you've probably heard of without necessarily connecting it to skin color at all: folate. Folate is a B vitamin that's absolutely essential for healthy cell division and development, particularly critical during pregnancy for proper fetal development. Here's the key detail: UV radiation can break down folate in the body, and in regions with intense year-round sun exposure, unprotected skin would have left early humans vulnerable to folate depletion, which could have led to serious reproductive and developmental problems across a population over time. Darker skin, by blocking a significant portion of incoming UV radiation, helped protect folate levels, which made it a truly important survival and reproductive advantage in high UV environments. Not simply a matter of avoiding sunburn or looking a certain way. This is honestly one of the more underappreciated pieces of this whole story. Skin color, at its evolutionary core, isn't primarily about appearance at all. It's about a delicate biochemical balancing act involving UV radiation, folate preservation, and, as we're about to get into, another critical nutrient that pulls in the exact opposite direction. So if dark skin was so protective and important in Africa, why did any human population ever evolve away from it? The answer lies in human migration, and specifically in what happened once certain populations moved out of Africa and into regions with dramatically less intense sunlight, particularly higher latitude regions further from the equator with much weaker UV exposure, especially during long winter months. This is where the second critical nutrient comes into play: vitamin D. Vitamin D is produced in human skin through a chemical reaction triggered specifically by UV radiation from sunlight. It's essential for calcium absorption, bone health, and a wide range of other important bodily functions. In regions with strong, consistent sun exposure, dark skin doesn't create a meaningful vitamin D problem, because even with melanin blocking a significant portion of incoming UV rays, there's still more than enough sunlight getting through to trigger adequate vitamin D production. But once populations migrated into higher latitude regions with weaker, more seasonal sunlight, that same protective dark skin, so beneficial back in high UV Africa, became a liability. Blocking too much of an already limited amount of UV radiation meant insufficient vitamin D production, which, left unaddressed over generations, could lead to serious health problems, including bone deformities, weakened immune function, and reduced reproductive success. So you end up with a remarkably fascinating evolutionary tug-of-war, playing out differently depending on geography. In high UV regions near the equator, the priority was protecting folate levels and preventing UV damage, which favored darker skin. In lower UV regions further from the equator, the priority shifted toward maximizing vitamin D production from limited available sunlight, which favored lighter skin, since less melanin meant more UV radiation could penetrate the skin and trigger vitamin D synthesis. Skin color, across the entire span of human evolutionary history, essentially represents a population-level compromise between these two competing biological pressures, calibrated specifically to whatever amount of UV radiation a given region typically receives. Let's talk about how researchers actually figured this out, because it's not simply an assumption based on modern observation. Genetic research has identified specific gene variants directly linked to skin pigmentation, and scientists have been able to estimate roughly when certain lighter skin variants became widespread within specific populations by studying ancient DNA extracted from skeletal remains found across Europe, and Asia. This research has produced a detail that tends to truly surprise people. Lighter skin appears to have spread through certain populations much more recently than most people assume. In some cases, within just the past several thousand years, a relatively short window on the overall timescale of human evolutionary history. It's worth taking a moment to explain how scientists actually extract this kind of timing information from ancient remains, since it's easy to state lighter skin spread a few thousand years ago without appreciating just how much careful work goes into establishing a claim like that. Researchers extract tiny fragments of preserved DNA from ancient bones and teeth, then sequence and compare specific genetic markers known to be strongly associated with skin pigmentation in modern populations. By examining remains from multiple time periods and multiple geographic locations, scientists can build up a rough timeline showing roughly when and how quickly specific lighter skin gene variants became common within a given population, rather than relying purely on guesswork or assumption based on where a population happens to live today. This kind of ancient DNA analysis has advanced enormously over the past couple of decades, and it's completely reshaped a lot of assumptions people previously held about the pace and timing of human evolutionary changes, skin color very much included. This timing detail is honestly one of the more remarkable parts of the story, because it means for a significant stretch of time after certain human populations had already migrated into Europe, they likely still had notably darker skin than most modern Europeans do today. Genetic evidence from ancient skeletal remains in parts of Europe, dated to several thousand years ago, suggests some of these populations retained darker skin pigmentation for thousands of years after settling in the region, well after you might intuitively expect lighter skin to have already evolved, given how long they'd already been living somewhere with much weaker sunlight than their African place of origin. Which raises an interesting question. If lighter skin was such a clear evolutionary advantage in low UV regions, why did it take so long to actually spread widely through certain populations after they'd already settled in these environments? Part of the answer likely comes down to diet. Populations with consistent access to vitamin D through their diet, particularly through fish, which is naturally rich in vitamin D, would have faced significantly less evolutionary pressure to develop lighter skin, since they were already getting adequate vitamin D through food rather than needing to rely primarily on sunlight-triggered skin production. Some researchers propose that coastal and fishing-based populations may have retained darker skin longer, specifically because their diet was already compensating for reduced sun exposure, reducing the urgency of the evolutionary pressure that would otherwise push toward lighter pigmentation over successive generations. Once agriculture spread more widely across Europe, however, and diets shifted increasingly toward grain-based staples with much lower natural vitamin D content, that dietary buffer would have largely disappeared. Suddenly, populations that had previously been getting sufficient vitamin D through fish or other dietary sources needed to rely much more heavily on sunlight-triggered skin production instead. And this shift appears to line up reasonably well with the timeline suggested by genetic evidence for when lighter skin variants started spreading more widely and rapidly through these populations. This is a remarkably elegant piece of the puzzle once you see how it fits together. It wasn't purely about migrating into a region with weaker sunlight and then automatically evolving lighter skin over time as a simple, direct response. Diet played a significant, actively shifting role in how much evolutionary pressure actually existed at any given point, meaning the transition to lighter skin was tied not just to geography and latitude, but to the specific evolving relationship between available sunlight and available dietary vitamin D sources within a given population. It's worth pausing on just how serious a vitamin D deficiency can actually be, because it's easy to hear bone health and assume this was a fairly minor, manageable problem for ancient populations. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Severe, prolonged vitamin D deficiency during childhood can lead to a condition involving soft, weakened, improperly formed bones, which in a pre-modern context without any medical intervention could mean serious mobility problems, skeletal deformities, and, for women specifically, a pelvis that failed to develop properly enough to make childbirth safe. That last detail matters enormously from an evolutionary standpoint, because anything that meaningfully reduces successful childbirth outcomes creates significant significant, direct pressure on a population's reproductive success over successive generations. This wasn't some minor cosmetic health issue quietly affecting a small handful of individuals. It was a serious population-level pressure capable of measurably affecting how many offspring survived and reproduced successfully within a given community, generation after generation. This helps explain why the evolutionary pressure toward lighter skin in low UV regions was strong enough to actually produce a lasting genetic shift, rather than simply being a minor inconvenience populations could tolerate indefinitely without any real biological cost. Evolution doesn't respond meaningfully to small cosmetic disadvantages. It responds to pressures that measurably affect survival and reproduction, and a nutrient deficiency capable of impairing childbirth safety across an entire population certainly qualifies as exactly that kind of pressure. There's another interesting piece of this story worth mentioning, involving the human ability to tan, meaning the skin's capacity to temporarily increase melanin production in response to sun exposure. This ability appears to have persisted across the vast majority of human populations, regardless of a population's typical baseline skin tone, and it represents a kind of flexible, short-term backup system layered on top of the longer-term evolutionary adaptation of baseline skin color itself. Tanning allows an individual's skin to adjust somewhat to seasonal changes in UV intensity within their own lifetime, offering additional protection during periods of particularly strong sun exposure without requiring any permanent genetic change. It's a neat example of how human biology developed both a slow, generational adaptation, baseline skin tone shifting gradually across many generations in response to a population's typical environment, and a much faster individual-level adaptation, temporary tanning in response to whatever conditions a specific person happens to be experiencing at any given point in their own life. Freckling is a related, smaller-scale phenomenon worth a brief mention too, particularly common in some lighter-skinned populations. Freckles represent localized, concentrated patches of melanin production, essentially small, individual spots of extra sun protection appearing on specific parts of the skin most frequently exposed to sunlight. It's a smaller-scale, more localized version of the same basic underlying biological principle driving broader skin tone variation, melanin concentrating specifically where and when additional UV protection happens to be useful for that particular individual. Let's also touch on hair and eye color for a moment, because they're closely connected to this same broader story in ways that often go unmentioned. The genetic pathways involved in skin pigmentation frequently overlap significantly with those responsible for hair and eye color, which helps explain why populations that evolved lighter skin in response to reduced UV exposure often show a correspondingly wider range of hair and eye colors as well. Lighter hair and eye colors becoming more common in certain populations appears to be, at least partly, a kind of genetic side effect connected to the same broader relaxation of selective pressure toward heavy, uniform pigmentation that occurred once populations moved into lower UV environments where intense, uniform pigmentation was no longer as strongly favored by natural selection. Let's talk about a related, often overlooked piece of this story: East Asian population, because the evolutionary path toward lighter skin in East Asia appears to have followed a somewhat different genetic route compared to the specific gene variants responsible for lighter skin in European populations. This is a great example of convergent evolution, where separate populations facing broadly similar environmental pressures involving reduced UV exposure at higher latitudes independently evolved toward a broadly similar outcome, lighter skin, but through different underlying genetic mechanisms rather than through some shared common genetic pathway inherited from a single common ancestor after leaving Africa. This detail matters because it reinforces something important about how evolution actually tends to work when different populations face similar environmental pressures in relative isolation from each other. Nature doesn't necessarily arrive at identical solutions through identical mechanisms every single time. Sometimes, similar environmental pressure produces a broadly similar visible outcome, lighter skin in this case, while the actual underlying genetic changes responsible for that outcome differ meaningfully between populations that evolved separately, without direct genetic exchange between them, at least regarding this specific trait. It's worth pausing here to address a common misconception directly, because this entire topic gets misunderstood constantly in casual conversation. Skin color has absolutely nothing to do with any meaningful difference in intelligence, capability, or worth between different human populations. It's purely a surface-level adaptation to a specific, measurable environmental pressure involving UV radiation levels and the competing biological demands of folate protection versus vitamin D production. Every population on Earth evolved skin pigmentation appropriate to the the specific UV conditions their ancestors experienced over many thousands of years, and that's the entire extent of what skin color evolutionarily represents. It's a solar adaptation, nothing more, and treating it as evidence of anything beyond that badly misrepresents what the actual scientific evidence shows. Let's bring some additional nuance into this by talking about populations that don't neatly fit the simple closer to the equator equals darker skin pattern, because there are some truly interesting exceptions worth mentioning. Populations in the Arctic, despite living at extremely high latitudes with correspondingly weak sunlight for much of the year, didn't necessarily evolve toward the lightest possible skin tones you might expect given the latitude alone. Traditional Arctic diet, historically rich in fish and marine mammal fat, both excellent dietary sources of vitamin D, likely reduced the evolutionary pressure toward extremely light skin, similar to the coastal fishing populations mentioned earlier in the European context. This is a solid reminder that latitude alone doesn't fully determine the evolutionary outcome. Diet, migration history, and the specific timeline of when a population settled in a given region all interact together, producing a more complicated overall picture than a simple, single-factor explanation would suggest. There's also an interesting angle worth mentioning involving sexual selection, meaning mate preference, alongside the environmental and dietary factors already discussed. Some researchers propose that once lighter skin began appearing within certain populations for the environmental and dietary reasons already covered, cultural or aesthetic preferences may have additionally reinforced and accelerated the spread of that trait within specific populations, layering a social selection pressure directly on top of the underlying environmental one. This remains a more actively debated area of research compared to the folate and vitamin D explanations, which rest on considerably more direct, measurable biological evidence, but it's a reasonable additional factor that many researchers consider plausible as a contributing influence, even if it likely wasn't the primary driver behind the overall pattern. It's also worth mentioning South Asian populations specifically, because they present another interesting variation on this general pattern. Many South Asian populations live at latitudes with fairly intense sun exposure, similar in some ways to equatorial Africa, yet show a considerable range of skin tones across different regions and communities. This variation appears to be shaped by a combination of factors including migration history, since some ancestral populations moved into the region from areas with different original UV exposure levels, alongside more localized environmental differences like elevation and cloud cover that can meaningfully affect actual UV exposure even within a broadly similar latitude range. It's a solid reminder that distance from the equator is a useful general predictor of skin tone patterns across large populations, but it's not a perfectly precise rule on its own, since plenty of local environmental and historical factors can shift the picture in specific regions. There's also a broader evolutionary lesson embedded in this entire story worth drawing out explicitly. Skin color is sometimes presented in oversimplified popular explanations, as though it evolved through some single, clean, linear process. Dark skin near the equator, lighter skin further away. End of story. The actual research paints a considerably messier, more interesting picture involving competing nutritional pressures, dietary buffering effects, migration timing, convergent evolution through different genetic pathways, and possibly even social or aesthetic reinforcement layered on top of all the underlying biology. This kind of layered complexity, several different forces interacting and sometimes working against each other rather than one single tidy explanation covering everything, turns out to be a pretty common pattern across a huge range of human evolutionary traits, not just skin color specifically. Let's zoom out and pull all of these threads together, because the full story turns out to be a lot more layered than the simple version most people have probably heard before. Human skin color didn't start out varied. It started dark, shaped by intense equatorial sun exposure and the corresponding need to protect folate levels critical for healthy reproduction. Once certain populations migrated into regions with significantly weaker sunlight, a new competing pressure emerged: the need for adequate vitamin D production, which gradually favored lighter skin in those specific environments. The exact timing and pace of this shift toward lighter skin was further shaped by diet, since populations with strong dietary sources of vitamin D faced less urgent pressure to evolve lighter pigmentation quickly. Different populations facing broadly similar environmental pressures in different regions of the world sometimes arrived at similar outcomes through entirely different underlying genetic genetic pathways. And additional factors like mate preference may have layered on top of all of this, further reinforcing patterns that were already being driven primarily by environmental and dietary pressures. None of this happened quickly, and none of it happened uniformly. Skin color across all of human history represents an ongoing, still continuing biological negotiation between two competing needs: protection from excessive UV radiation and adequate production of a critical vitamin, calibrated specifically to whatever combination of sunlight and diet a given population's ancestors happened to experience over an enormous stretch of evolutionary time. So the next time you notice the sheer range of skin tones present in any group of people, it's worth remembering that you're looking at a visible, physical record of thousands of generations of human migration, environmental adaptation, and dietary history, written directly into the skin of populations that spread out across nearly every environment the planet has to offer. What looks like simple, surface-level variation is actually one of the clearest, most well-documented examples of evolution responding directly and measurably to environmental pressure, playing out across the entire span of human migration and settlement. Which leaves an interesting thought worth sitting with. If something as visible and immediately obvious as skin color turns out to be this recent, this specifically tied to migration, diet, and geography, rather than some deep, fixed, unchanging trait. What other visible human characteristics that feel completely fixed and permanent might actually still be quietly shifting, shaped by environmental pressures we haven't even fully identified yet?